Today, we're pulling back the curtain on the secret language of computers. We're going to peel back the layers of your screen, your apps, your files, and look at how computers actually see the world. And spoiler alert, it's not in images or text, but in a simple, elegant system of ones and zeros. So, let's dive in.
So it all really comes down to this one simple question. How is it possible? I mean, think about it. The incredibly rich, complex digital world we live in is built on something as basic as a light switch. How do you go from a simple on or off to streaming a high-def movie or connecting with someone across the globe? Well, that's the puzzle we're going to solve today.
You see, the answer starts with the physical hardware itself. It's not that computers chose to use a complicated system. They're just speaking their native language, a language that's dictated by the way they're built.
Deep down, at the very heart of every single computer, are millions, sometimes billions, of these microscopic switches called transistors. Now, each one can only do two things. It can be on, letting electricity flow through, or it can be off, stopping the flow. That's it. There is no kinda on. This physical reality forces the entire system to be built around this simple two-state idea.
And if your hardware only has two states, you need a language with only two symbols. And that language is binary. We just decided to represent the on state with a 1 and the off state with a 0. Every single thing a computer does, every letter you type, every pixel on this very screen has to be translated into a long string of these ones and zeros for the hardware to have any idea what's going on.
Now, computers are totally fluent in binary, but us humans? Not so much. Trying to read endless strings of ones and zeros is just a recipe for a headache. So, to make life easier for us, we use a couple of other number systems that act as a bridge between our world and the computers. Let's break them down.
So here are the three main players. You've got denary, or base 10, which is what we use every single day. Then there's binary, base 2, the computer's language. And then there's this really useful one called hexadecimal, or base 16. Now you might notice something weird. Hexadecimal uses the letters A through F. That's because it needs to represent the numbers 10 through 15 with a single character. And this is its superpower. It can pack a ton of information into a small space, which makes it a perfect shorthand for long, clunky binary code.
So how do we actually translate between our language and the computer's? Let's take the number 165. We just use the place values of binary, 128, 64, 32, 16, and so on. We just ask a series of simple questions. First, does 128 fit into 165? Yep, it sure does, so we put down a 1, and we're left with 37. Next, does 64 fit into 37? Nope, so that's a 0. Does 32 fit? Yes, that's another 1. You just keep doing that all the way down, and pretty soon you get your 8-bit binary number, 10100101.
Okay, that's great for positive numbers. But what about negative numbers? Well, for that, computers use a really clever system called 2's complement. And the absolute key to understanding it is the leftmost bit, what we call the most significant bit, or MSB. In a normal positive number, that bit is worth plus 128. But in 2's complement, we change its value. It becomes negative 128. And just by making that one tiny change, we can suddenly represent a whole range of negative numbers. And listen up, because this is so important, especially if you're studying this. A super common mistake is to just find the binary for a positive number and try to stick a minus sign on it. That will not work. You have to use the 2's complement system, where that first bit is treated as negative 128. Get that wrong, and all the computer's math falls apart.
Okay, I know, this can all feel a little abstract, but trust me, these number systems are constantly working behind the scenes in pretty much every piece of technology you use.
Hexadecimal, in particular, is an unsung hero. Once you know what to look for, you'll see it everywhere. It's used for the unique MAC address that identifies your phone or laptop on a network. It's used for those super long IPv6 addresses that basically run the modern internet. It's used to define colors on websites, and it's used for those cryptic error codes that help programmers figure out what went wrong. It's really the perfect bridge for us humans into the machine's binary world.
I mean, take a look at this. You've probably seen something like it before. It's an HTML color code. The hashtag just tells the browser, hey, what's coming next is hex. Then, the first two digits control red, the next two control green, and the last two control blue. So in this case, we've set red and green to 0, completely off, and we've cranked blue all the way up to its maximum value, FF. And what do you get? A perfect, pure blue on your screen.
But this binary world isn't infinite. It has limits. For example, an 8-bit register can only hold a number up to 255. So what happens if you try to add, say, 200 and 100? The answer is 300, right? But the computer literally has nowhere to store that number. It would need a 9th bit, which doesn't exist in an 8-bit system. This causes what's called an overflow error, and it leads to a totally wrong answer.
But computers do have a really cool trick up their sleeve for doing math super fast. It's called a logical shift. By just taking all the bits in a number and sliding them one spot to the left, you instantly multiply the number by 2. Slide them 2 spots, you multiply by 4. And you guessed it, shift them to the right and you're dividing by powers of 2. For a processor, this is a blazingly fast and efficient way to do calculations.
All right, so we've been talking a lot about numbers. But what about everything else? How does this system of ones and zeros represent the music, the text, and the images that make up our digital lives? Let's take a look.
Well, for text, we started out with systems like ASCII. It uses 8 bits, which gives it 256 possible combinations. Plenty of room for every letter, number, and symbol in English. But the world is a lot bigger than just the English alphabet, right? So along came Unicode. By using more bits for each character, Unicode has enough space for every character from every language on Earth. Plus, and this is important, all the emojis we use every day.
Now, sound is a little different. It's an analog wave in the real world. To turn it into digital data, we have to take thousands of tiny snapshots or samples of that wave every single second. That's called the sampling rate. Then, for each snapshot, we use a certain number of bits to measure how loud it was. That's the sample resolution. And here's the trade-off. The more snapshots you take and the more bits you use for each one, the better it sounds, but the file size gets way bigger.
And you'll see a really similar idea with images. A digital image is just broken down into a giant grid of tiny dots called pixels. The total number of dots, the width times the height, is the resolution. And then the number of bits we use to store the color of each one of those individual pixels, that's the color depth. So a 24-bit color depth, for instance, gives you over 16 million possible colors for every single pixel in the image.
So, we figured out how to turn our entire world into ones and zeros. Now we have a new problem. How do we measure all this data? How do we store it? And how do we manage it so it doesn't take up all the space in the universe?
You might think that in our base 10 world, the important numbers are 10 or 100 or 1,000. But because computers are built on powers of 2, the real magic number is this one, 1,024. That's 2 to the power of 10, and it is the foundation of all modern data measurement.
And this is a really critical point. We often hear the word kilobyte and our brains just think 1,000. But in the world of computing, the technically correct term is a kibibyte, and it is always 1,024 bytes. A mebibyte is 1,024 kibibytes, a gibibyte is 1,024 mebibytes, and so on. If you're studying this, using 1,000 instead of 1,024 is a mistake you really don't want to make.
So how do we actually use this stuff to figure out file sizes? Well, the formulas are pretty straightforward. For a sound file, you'd multiply the sample rate by the resolution and then by the length of the sound in seconds. For an image, you just multiply its width by its height to get the total number of pixels, and then multiply that by the color depth. The only catch is, both of these give you an answer in bits, so you have to remember to divide the final number by 8 to get the size in bytes.
Of course, these files can get absolutely massive, which is why we have compression, and it really comes in 2 main flavors. You've got lossless compression, like you'd find in a PNG file. It uses clever tricks like run-length encoding to shrink the file without deleting a single bit of data. You can always get the perfect original back. Then you have lossy compression, which is what JPEGs and MP3s use. It makes files way smaller by permanently throwing away data it decides you probably won't notice is gone. The trade-off? You can never, ever get that original quality back.
So when you really step back and think about it, it's kind of mind-blowing. Our entire, vibrant, interconnected digital world is built on a foundation of just flipping simple switches on and off, just really, really fast. It's a whole universe created from a language with only 2 states, which kind of leaves you with one final big thought. If we manage to build all of this with just 2 states, what happens when we finally invent a third?